So looking at current modulation, so as I said, modulation allows us to kind of create different aspects with the waveforms to basically get specific clinical effects. So anytime you hear the term modulation, it kind of can mean different things based upon what it is you're trying to modulate or change with the waveform or electrical current that you're using. So as we stated, most forms of electrical stim that we're going to use are pulsed waveforms. Okay, and the reason for that is it's difficult to use one of the two pure waveforms for most of your therapeutic effects. Again, there are versions of that, but most of them are going to be pulsed. So they're going to have what are called phases, as we previously described. The timing is something that can be modulated as well. So that's where you affect the phase duration or the pulse width. So those two things both impact one another. The pure definitions of them are different, but really whenever you hear the term phase duration or pulse width or even pulse duration, for the purposes of the electrical currents, they all kind of mean the same thing when you're setting them. So for instance, if you remember when we had the small tens units, and I showed you the dial that changed the pulse duration, that was basically, again, anytime you change that, that also affects phase duration, pulse width. It basically looks at how wide are the pulses, and that's going to be an important clinical parameter when you're setting that. The other thing that could be modulated is the intensity. Now, we set the intensity, but there can also be times where that can be varied as well. And from a definition standpoint, intensity is the amplitude of the current. Okay, so those are all different things that, again, we could kind of manipulate with the therapeutic currents that we're going to be talking about. So when we look at pulse and phase characteristics of different types of electrical current, so one of the things that you're going to have to be responsible for, like you will have to be responsible for describing current. So in other words, I'll literally have on the exam a picture, and you'll have to be able to describe parts of the current. So that includes the shape of the current, whether it's pulsed, those types of things. So here we're going to look at the phase shape. And again, what's important about the phase shape is it kind of tells you the characteristics of the waveform that you're applying. So if we look on the top, that's a sinusoidal shape, and that's reminiscent of what we looked at with our pure alternating current. In the middle, we have a rectangular current, and you see there representative of a pulse. And on the bottom, you have a spike, or what sometimes they also call a twin spike. Now, what's interesting about that, when we talk about pulse and phase characteristics, when you look at that, you're only seeing movement in one direction. However, you would not classify that as a DC current. The reason why you wouldn't classify it as a DC current is because it's interrupted. And we'll talk about how you would classify something like that. Obviously, the two up top alternate between the positive and negative poles. The one on the bottom does not. But we'll talk about, again, how we would classify that, because you would not say, well, it's in one direction, it's DC. It can't be DC because it's pulsed. But we'll talk about the characteristics and how that gets described later on. So pulse and phase characteristics, and again, kind of reference the picture as I kind of go through what we're looking at here. So a pulse is a period of charged particle movement. So if we look there, you can see what constitutes a pulse in the case of the current that we're looking at here. A phase is just the unidirectional movement. So when we're talking pulse and phase characteristics, those are that's the terminology that we'll be using for that. You also have on there the interpulse interval. Okay, so the interpulse interval is when you have a current that is not a continuous current. That's the time period between the two pulses. So we have two pulses present in the picture that we're describing here. they're broken up by an interpulse interval that would then basically make it a pulsed current, obviously, because it's not continuously flowing. So as I was talking about earlier, so we talk about pulse width, phase duration, pulse duration. They kind of all mean the same thing clinically in basically how wide the pulse is going to be. Okay, as far as the descriptor, you have to look at what you're impacting. But from the clinical perspective, so for instance, we talked about in lab doing frequency and then the pulse width, and that basically tells you how long those individual pulses are going to last, which is then going to impact your treatment response. And we'll see later on kind of what you would look to set both of those at, again, in looking at the clinical effects that you're looking to get from it. So some more characteristics of the pulse and the phase. So we have three types of categories based upon how many phases you have. So you have a monophasic, a biphasic, and polyphasic currents. Now if you look on the picture here, we have a biphasic, meaning that you have two phases, so you have both a positive and negative. Remember we said when we're looking at these pictures, above the line is positive, below the line is negative. If you were to have a monophasic, you would have only current flow in one direction. So if we were to get rid of one of those phases, you would then have a monophasic, current. Now remember, so I showed you the direct current. So direct current is monophasic, okay, because it's only in one direction. But not all monophasic currents are necessarily direct, okay? So if I showed, remember going back to the picture of the spiked shaped current. That's monophasic, but it's not a direct current because there's a pulse, okay? So that would be monophasic, but not direct. But all direct currents are monophasic because they're always flowing in one direction. So your monophasic would be 1, biphasic is 2. You also have polyphasic. So what's polyphasic? That's when you have many phases put together. An example of a polyphasic current, when you see later on when I'm showing some of the pictures of the waveforms, would be your Russian current, okay? Because what happens there is you get a bunch of phases kind of bunched together. That's when you have a polyphasic current. So it's basically more than 2. Okay, so monophasic 1, biphasic 2, polyphasic more than 2 or many phases kind of bunched together. Some other pulse and phase characteristics. Again, reference the picture on the side here. The phase charge is the total electrical charge of a single phase. Okay, so if we again, you got to tie in your terms together. So make sure you still understand what a phase is. The pulse charge is the total amount of electrical charge of a single pulse. Okay, so when we're looking at the total pulse, it's the charge of the entire pulse. The pulse symmetry and charge balance are kind of related. So the pulse symmetry looks at how symmetrical is it, both looking at the positive and negative. So if you look at the picture on the side here, representative of two different pulses. You have two biphasic pulses. One is balanced and symmetrical. The other is unbalanced and asymmetrical. Okay? And the charge balance looks at the relationship of the charges. So those two things kind of relate to each other, the pulse symmetry and the charge balance. So when you look at the picture, again, if you look at the balanced and symmetrical biphasic pulse, you have both the phase charge and the pulse charge are equal, okay? Whereas in the unbalanced and asymmetrical, they're different. So if you look at the positive and negative on that one, the positive has a much higher amplitude and a much bigger pulse width than the negative. Okay, so that would be an unbalanced and asymmetrical. And again, that would impact basically what your end result would be as far as your therapeutic response in the pulse and phase characteristics. Another thing to kind of look at, and this would relate to an alternating current. So when you can get a repetitive series of pulses at a fixed frequency, what you basically do is create what they call a train of alternating current, where basically you pack them into bursts. Okay, so it's a repetitive series of pulses at a fixed frequency, and the interval is the time in which the burst occurs. So if you look at the picture on the side, we've basically taken an alternating current and we've kind of packaged, if you will, the pulses into small bursts of electrical current with an interburst interval, where there's a time period where the current will not be flowing. So you do this with certain types of electrical current. As you see with some of the waveforms, you will see where this becomes a characteristic of the actual application of the individual waveforms. So we call these things pulse trains, where again we basically group the pulses in bigger packets of energy, and they get released during the intervals where the electrical current is actually flowing. For current timing modulation, so these are some of the things that you can do with the timing, and I kind of described this earlier. This is a lot of what you're actually going to manipulate with the treatments to create a desired effect, be it for different levels of pain control, for different sensory responses, different types of muscle contraction. So the duty cycle is the time in which current is flowing. Now, again, as I talked about in the lab, there's two different types of duty cycles. There's the intrinsic, which is characterized by kind of how the unit controls that. And then there's the extrinsic, that you as the clinician control the actual physical on-off time of the current. Okay? So there's two different types of duty cycles. So both of those are going to impact the treatment. The intrinsic will be something a little more particular to the unit, and we'll kind of see how that works later with the different waveforms. The pulse duration, now again, pulse duration, pulse width, phase duration, it basically all impacts how wide the pulse is, okay? So we have what we would call a short pulse duration, which is anything less than 150 microseconds, and we have a long pulse duration, which is anything greater than 200. So we'll talk about how you would set a short versus long pulse duration based upon the type of effect you want to get. You have the interpulse interval, which is the time in between the pulses as they get delivered to the patient. You have the rise and decay time, which we'll talk about. We kind of talked about how that works already, but that's basically the time from the start of the phase to the time that it reaches the peak of the amplitude or the peak intensity, and then the decay time is from the max amplitude until the end. So if you look at the picture, again, 0 is kind of the isoelectric line, that's where it starts. So from the time that it goes up to the peak, that's the rise, and the decay time is from the max until the end, until it returns to the isoelectric or the 0 line. That's the decay time, okay? Pulse period is the time in which the pulse is working, and the pulse rate is the frequency at which it occurs, okay, or the pulses per second. So that's how many pulses per second that you're actually setting your time for. Okay, then your amplitude modulation. So current amplitude refers to intensity. So when we talk about, turning the intensity up, so literally what you do with the units when you're actually turning up the intensity to the point where you're getting your effect, whether that's a strong sensory or a motor effect, that's your intensity. different ways that could be modulated are dependent upon some of the characteristics of amplitude. So again, looking at the diagram or the picture on the slide, you have your peak amplitude, which is basically the point of the highest intensity. You also have your average amplitude. Now, the average amplitude ends up being kind of a product. If you look at the picture, you see the peak to peak. So we have an alternating current here. The average amplitude looks at the average between the positive and negative. So you see what the result of that ends up being based upon the positive and negative flow plus the on-off time. So the average amplitude, as depicted by the dotted line, you look at the peak, because of the fact it's an alternating current, that creates a different average current. Okay, so you have the peak-to-peak amplitude, and you have the average amplitude based on the size and shape of the waveform as it's depicted in the picture.